Let us just finish this one. Okay, what do we know here? Now, I know that the expected waiting time equals to this quantity where only S1 shows up, and we also know that S1, the first inter-arrival time for this homogeneous Poisson process, has exponential distribution with mean 1 over lambda. Okay, and either you would just actually do all the calculations yourself, I mean, for both numerator and denominator, or actually you can use the following trick. Okay, the following trick. Now here you have an indicator in the variable, right? And this is 1 minus the indicator random variable of the complement of the event sitting over there. So I will just write then that as S1 times 1 minus the indicator of the event that S1 is greater than or equal to T. Okay? And then we divide by the probability that S1 is greater than or equal to T. The reason I do that is from the second part, when you divide by this, you will get a conditional expectation, and conditional expectations are easier to calculate for memorylessness random variables, namely exponential or geometric. Right? The other one gives you an unconditional random variable for which we also know the mean. So evaluating this is a lot easier than this one. Here I should just take this expectation alone, and it just gives an integral. You have to do partial integration and so on and so forth, which is not really so much interesting. So if we just now distribute this over these two random variables, and then take the expectation, then you have expected value of S1 minus the expected value of S1 on the event that S1 is greater than or equal to T. And of course we divide by the probability that S1 is greater than T. Okay, then you have expected value of S1, which is 1 over, okay, maybe I should first write it so that we see what happens to the second term, in fact. Now, if you divide this expected value by this probability, you remember that the expected value of any random variable x on any event A divided by the probability of the same event A is nothing but the condition expected value of this random variable given that event A has happened. Right? We use that. So event A is, in this case, that S1 is greater than or equal to T. Random variable X, in this case, is inter-arrival time S1. So this is the expected value of S1 given S1 is greater than or equal to T. Okay? Now, why is this easier to calculate? Now, we did this, I guess, once in class. So now you can write this one as T plus S1 minus T. So this is the excess over T of random variable S1, which is non-negative if you are told that S1 is greater than or equal to T. Right? Expected value of the sum given this is the sum of expected value of T and sum of the expected value of S1 minus T given this. So then this thing is going to be T plus the expected value of S1 minus T given S1 is greater than T, right? And since S1 has exponential distribution, namely it is memorylessness, it has memorylessness property, this conditional excess, the conditional distribution of this excess lifetime is the same as the unconditional expected, unconditional distribution of the same random variable S1, right? So S1 minus T given S1 is greater than T has the same distribution as S1, unconditional distribution of S1, right? And therefore the expected value, conditional expectation here is the same as, right, the unconditional expectation of random variable S1. and we don't forget, of course, adding t, and then this equals t plus expected value of 1 over s is 1 over lambda. So we now know what the result for this one is, right? And we are fine, right? And here, what do we have? Well, expected value of the same exponential random variable is 1 over lambda, and this is, we calculated in part A, e to the minus lambda capital T. Right? If we just put everything together, you have e to the minus, not minus anymore, right? It is e to the power lambda T divided by lambda, and minus T coming from here, minus 1 over lambda. So that's the result. Okay? So that's the result. I guess you may look at this one and ask to yourselves whether this can ever be negative, because just to check whether your result makes sense or not, you can put everything under the common parenthesis of 1 over lambda, right? So this comes e to the lambda t, right? Then there is minus 1, then there is minus lambda times t. Okay? So we can write it like this. And we know that this is what? 1 plus lambda t plus still some positive terms. So the term that you subtract is only part of this thing. So this is always going to be positive. So this at least makes sense as a positive number. I guess the calculation is also correct. So this is the expected average, expected waiting time until this woman crosses this thing. Okay? I don't know whether she is still waiting there while we were doing this calculation. It took a while, right? It took a while. But I guess it's a good exercise. But unfortunately, I misjudged. I forgot that I didn't really discuss this. But now it is time to discuss this thing. And at least we learn how to use it. Now let's see why this is correct. Do we have any questions about the calculation or the formulation? Okay. Okay. So, showing that the inter-arrival times of a Poisson process are independent, identically distributed exponentials is one thing, and there are similar characterizations of arrival times as well. So we will be looking at all of this next. Okay, we will be looking at the distributions associated with a Poisson process. Okay. So we will take any Poisson process X. Okay. I guess in this part of the lecture I will be looking at the homogeneous Poisson processes with some rate lambda, let's say, and we use this notation to denote what? The number of arrivals, let's say, until time t. We will also use this alternative notation. X assigned to interval from s to t, meaning this is nothing but xt minus xs in terms of the old notation. Sometimes it is easier to identify disjoint intervals if you use this notation than this one. So alternatively, I will use both of these. Okay, and of course, this just is what the number of events in the interval from s to t. Okay, and then we will use Wn to denote the arrival or the end arrival time. Okay, and arrival time. or nth event time. And I'll use the same S that we introduced earlier to denote the nth inter-arrival time. So this is Wn minus Wn minus 1. So this is nth inter-arrival time. So we can label all these things in a picture, right, at time 0. So we have the first time of the first arrival, then time of the second arrival, time of the third arrival, let's say. It goes like this, right? And this is the first inter-arrival time, okay? And by convention, we usually choose W0 equals 0, okay? It doesn't, it is not really an arrival time, but for this to make sense, when n equals 1, we just set it to 0. Okay? And this is then a second inter-arrival time. This is the third arrival time. And it goes like this. Okay? Now we are going to describe the distribution of random variables W and Sn. Okay? And the first result says, okay, for a homogeneous Poisson process, we always have homogeneous Poisson process in mind as we state these theorems. Similar things can be done actually for the more general process, but they do not always look nice. Okay, Wn, right, the nth arrival time has gamma distribution. Okay, you may not remember its probability density function. I am going to write it here, whose probability density function is actually hidden in the following, in this expression. This is not like the density function, but I still like to write it like this. Okay. So what is this? The probability that Wn, the nth arrival time, happens near time t, right? We remember this. This is density function times the length of the interval, which is dt in this case, right? And the density function, and I'm going to put this in a little unusual way, which will, after you see the derivation, that will help you remember the density as well. This is like the lambda times t to the power n minus 1 divided by n minus 1 factorial times e to the minus lambda t. What is this? This is actually not gamma, but it looks like Poisson. So this is actually the probability that there will be exactly n minus 1 arrivals until time t, right? Times lambda dt. Now we will see that for the nth arrival time to happen near t, first of all you must have exactly n minus 1 arrivals before time t, and there must be an arrival just around time t. That's the product. Therefore you have this Poisson stuff. Right? Now you are always telling me that you don't remember the gamma distribution. Now you cannot forget it. Right? If you just think gamma distribution as actually the distribution for the nth arrival time, so then what is happening? For the nth arrival time to be near t, right? You must have exactly n minus 1 arrival time. You must have exactly n minus 1 arrivals till time t with this probability times, then you must have an arrival right to next to time t in the next dt units of time. Okay? This might be not quite clear, but we'll see that. So this is infinitesimal probability. Okay. And the density function, what is the density function? It is actually this part. Right. Okay. What did I do? Okay, let me see. I guess I have everything here. From here, you can at least get a clue about the distribution of inter-arrival times, because when you rewrite the same formula for n equals 1, right, you see that the first arrival time is the same as the first inter-arrival time. So we can actually at least get an upfront view of what the distribution of these guys are gonna be. Still, of course, this doesn't tell us immediately that all these things are independent, identically distributed, but at least now you can see that the first arrival time, which is the same as the first inter-arrival time, equals to t, right, or is going to be near t with probability what? When you set n equals 1, this disappears, only this 2 remains, so lambda times e to the minus lambda t dt, which is the density of exponential times dt, right? So we know that. Of course, we have to still work hard to show that they are independent and they all have the same distribution. That's next, after we convince ourselves that this theorem is correct. Okay. All right. How do I do that? Well, let's look at this. It's an heuristic derivation, so it is not, possible to give the rigorous proofs for these things at this level of class. But we can heuristically still actually use, for example, independent increments property of independent increments property of Poisson process to derive this formula. Right? How do you do that? Before you worry about the probabilities, let us look at the following event. So what does it mean that the end arrival time is between, let's say, time t and t plus delta t for a very small delta t? Okay, what does this mean? So you draw again a picture. So there is time t and there is t plus delta t, right? So this is a small interval. I still draw it big so that we can see, but otherwise it's going to be small, right? So for Wn, the end arrival time to be here, right? We must have, right, with high probability, well, okay, then the event doesn't really work in this case. I should probably switch immediately to the probability, because some of the possibilities will have negligible probabilities, and we will want to just forget about them. Okay, for the probability that end arrival time is gonna squeeze between time t, or squeeze inside a very small interval right after time t, equals to what? So the probability that, first of all, you must have, if this is the place for the end arrival time, then you must have exactly n minus 1 arrivals, right, before this. So that means that, so x counts the number of arrivals, right, because it's the process that we started with. So from 0 to t, right, in this interval, how many arrivals you should expect? N minus 1. And this is still an interval, no matter how small it is. And for this to happen, you would expect with high probability that number of arrivals from t to delta t, t to t plus delta t, of course, equals exactly 1. So that one indicates the nth one fits here, right, because it follows the n minus 1 arrivals right before time t. And I guess that's enough. Okay. And of course there are some cases that I missed. This is not the only story for this one, but you remember from the first lecture on Poisson processes, we said inside a very small interval you can fit at most one arrival of a Poisson process. So in each of very small intervals, time intervals, there will be either no arrivals or at most one, or exactly one, right? Either no or exactly one, right? So this is that case. So there is exactly one, and having all other undesirable or more complicated cases can happen only with a very negligible probability. And we gather them all together in a dustbin. So we'll just throw them away, okay, in a moment. Okay, all right? Does this make sense? I guess intuitively okay. And then now we can do something about all of this. See, on purpose wrote this event in terms of the number of arrivals over disjoint intervals. Because interval from 0 to t is disjoint from the interval from t to delta t plus delta t. Since intervals are disjoint and x counts number of arrivals, so these are, we know that, independent because of what? Independent increment property of Poisson process. So you see that we keep using the same two properties of Poisson processes. But what can I do? They are the only two things that are given to me. Of course I am going to use them whenever I have a chance to do that, right? So therefore this joint probability is of course the product of probabilities of these marginal individual events. Okay. And then you ask to yourselves, what is this? Actually, I already announced it earlier, so it is exactly the probability that there will be n-1 arrivals, but we know that x number of arrivals in the interval 0 t has Poisson distribution with rate, what? Lambda times the length of the interval, which is t, right? So this is then lambda times t to the power n-1 divided by n-1 factorial times e to the minus lambda t. How about this part? Well, as before, of course, number of arrivals over this small interval still has Poisson distribution, but now with rate what? This is Poisson distribution with rate lambda times the length of the interval, which is a small number delta t. There is an opportunity to come up with a simple approximation as at least delta t goes to 0. Okay? That's what we are going to do. But first let us write the exact value for this. Namely, if it is 1, this is lambda times delta t to the power 1, namely itself, divided by 1 factorial. Okay, so 1 is still there. Times e to the minus lambda times delta t. Okay? And there is always these tiny things that will soon disappear when we first divide by delta t and let delta t go to 0. Okay. Now, is this going to simplify? Well, of course, you know that if delta t were 0, this quantity would be 1. So this quantity is close to 1, in fact. Even if delta t is not 0, if it is still close to 0, it's going to be close to 1. How close is it? It is 1 minus delta t plus still some other quantities that are far, far smaller than delta t. There is one term, delta t, already. If it is there, in comparison to this one, these are so small that you can just forget about them. And they will join to this part soon after we multiply. Okay? We know where does this come from? It's just the exponential function. You remember the first two terms. The first two terms that I get from there. Okay, then we distribute this over this. So this is all inside parentheses. If you multiply small terms with, well, still medium terms, they are still small, they will join here. So I am not worried about the result you get when you multiply this term with the remaining. They will all be pushed away into this. So we are only interested in this times this part. Okay. Lambda t to the power n minus 1 divided by n minus 1 factorial times e to the minus lambda t. And from here, what do I get? Lambda delta t, right? This times 1 minus lambda squared times delta t squared. That's also 1 order more than delta t, so it's going to go to 0 faster than delta t. That also joins to this block. Actually, what is this thing? O delta t, smaller delta t, contains every term, let's say f such, or f of delta t, any function of delta t, such that even after you divide by delta t, when you take the limit as delta t goes to 0, namely if you choose delta t small, this still goes to 0. Okay? One candidate for such thing, delta t squared. Delta t squared, you divide by delta t, one of the delta t's will survive in the numerator. If you let delta t go to 0, it will just vanish. That means that the delta t, well, that was an example. This is also equivalent to say that for small delta t, this f of delta is a lot smaller than delta t, so we can safely forget about it. Well, not safely, but it works, at least if you want to give a general idea what is going on. So, now lambda delta t times lambda delta t, now you get a delta t squared. So you get a term of this kind, so we can just have it counted toward this, which is going to be combined here. So in this product, I will only have one term that I would like to remember, that is lambda delta t times 1, and the remaining ones will be put all into this basket of small terms. Okay? Okay? We'll continue. I guess we are done. So you have this term times delta t plus all these terms which are a lot smaller than delta t. Okay? Then what I am going to do is just I'm going to divide by both sides by delta t and then let delta t go to 0. Why do I do that? Because I am trying to find the density function of this guy. So I first divide, so this doesn't mean anything. Right? And this equals, why did I do that? Okay. Unfortunately, I didn't be careful. Okay. If you divide by delta t, the right hand side, this disappears, so you have now something that doesn't depend on delta t anymore. Right? So lambda appeared plus O delta t divided by delta t. Okay. And then what am I going to do? I said I would like to find the density function, probability density function of W, and that is equivalent to doing what? You calculate the cumulative what was it? Distribution function of random variable Wn, right? That's what we are doing here. And then you take the derivative. If you take the limit as delta t goes to 0, that's exactly what you will be doing. So you take the limit here, and of course you take the limit of the right hand side as well as delta t goes to 0. This entire thing now, right? Then here you will find the density, okay? And the density will become, on the right hand side, this doesn't depend on delta t, therefore that survives. And what happens to this one? It goes to 0, right? So this contains all the terms of this kind. It is itself is also going to go to 0, right? So we get lambda times t. What is left is, okay, this goes to 0 as delta t goes to 0, and then you get only lambda t to the power n minus 1 divided by n minus 1 factorial times e to the minus lambda t times lambda. Right? And as I said, the easiest way to remember the formula is what? End arrival time has the probability the same probability as the probability of having exactly n minus 1 Poisson arrivals until time t, and then having exactly one event in the next dt units of time, which is given by lambda times the length of the interval dt. So this is actually a good approximation of lambda times dt times e to the minus lambda dt. If you want, it's the 1 factorial is here and 1 is here. Okay? So this is close to 1. dt means something very small to 0. Okay? Okay. Any questions? Huh? You are fine with it? Right. Okay. Perhaps then we can also look to the distribution of inter-arrival times. Let's discuss that as well and then finish today's class. we in fact play a similar game. If you already realize, if you already understood that Poisson events, right, can, over a small interval, you can have only 0 or exactly one Poisson event with respective probabilities, and the rest is just a trivial exercise in infinitesimal probabilities. Okay, it's another theorem which says that the inter-arrival times, right, inter-arrival times S1, S2, and so on, of the same homogeneous Poisson process we introduced at the beginning, are independent and identically distributed exponential random variables. Random variables with mean 1 over the rate of Poisson process, namely lambda. Okay? So how do we show this? Okay? We have to find what? We have to find the joint probability density function of, let's say, let us look for the first n random variables. N is going to be arbitrary, so you can choose arbitrarily large n to basically conclude that this result holds for any arbitrary collection of, finite collection of random variables, inter-arrival times. Okay? We would like to find this density function, okay? Joint density, okay, let me write it. The joint probability density function of S1, Sn, okay? And we know that this thing, when you integrate it, right, gives you the probability that together all these n random variables fall into the set over which you integrate the function, right? So this is an integral, right? This is an integral, height times the width again, or just the volume in this case. And this is what? The probability that random variables S1 through Sn are gonna be near the values S1 through Sn respectively. Namely, this is the same as the probability that S1 is between this small s1 plus this small interval around it, and S2 is between small s2 and S2 plus this small increment, right? It goes like this. Maybe I should just do like that. And then Sn, inter-arrival time is between these two small numbers. Okay? There might be a small difference between right and left sides, but there is also again a difference which goes to 0 after you divide by the product of this, or after you divide by the volume of this quantity. That's exactly the definition of the derivative. Derivative is obtained by the taking, or it's exactly the definition of the probability density function, right? By definition, it is what? The partial derivative of these joint probabilities with respect to S1, S2, S, so on and so forth. So you divide by this quantity, both sides. This, of course, disappears. So you divide this and you divide that one as well. When you let all these things go to 0, then this will converge to this one, and of course the remaining should disappear, and that's by definition of this small o notation. After you divide by its argument, if you let the volume to shrink to 0, it is going to go to 0. Okay? Okay, we have that. And now the trick is the same. So in order to be able to calculate this probability, we should be able to write the same event in terms of counts of Poisson arrivals over disjoint intervals. If they are disjoint, then joint probability of those intersection of events can be then written as a product of probabilities, and then we will use that the counts over disjoint intervals also have Poisson distribution, and then we will be doing a lot of simplifications because we are looking on the number of arrivals over small intervals and so on and so forth. It goes like this. Okay, what is the picture then in this case? So we have a line, real line, there is S1 here, then a small interval of length delta S1 here, then there is S1 plus S2, right? Why is that? So we know that the first inter-arrival time is of length S1, that means the first arrival time, which is the same as the first inter-arrival time, will fall in this interval because of this. So W1 is here, right? And the second arrival time is when? First inter-arrival time plus the second inter-arrival time, right? That's given S1 by S1 plus S2. Then there is this small interval S2, delta S2, okay? And then you have one arrival here. So the inter-arrival time is approximately S2, right? And arrival time, the second arrival time is going to be somewhere in this small interval. Then you get the picture, I guess. Now you will have S1 plus S2 plus S3. So this is when, this is near where this third arrival is going to take place. You have a small interval delta S2, delta S3, and there will be an arrival, right? W3 is going to be, this is the place 4, right? And it goes like this. And the last one is what? You have S1 through Sn sum, then you have a small interval delta Sn, right? Like this. And this is the place for the nth arrival time. Okay? And then what do I have? We will just write this one in terms of counts. For this to happen, so this is the time of the first arrival, this is the time of the second arrival. That means there won't be any arrivals here. Like the first one comes right inside this. And between this W1 and W2, of course, there cannot be any arrivals, right? Because this is the first, this is the second arrival. So there won't be any arrival between these 2 points either, because this is the second, this is the third arrival. So in between all these points, here there are dots, so we have to be careful, but you must have gotten the picture, right? Within these large intervals, between small intervals, there won't be any arrivals. Okay? So this is equivalent to saying that in big intervals there are no arrivals, in small intervals there are exactly one arrival. Okay? Exactly one, because we choose length of the interval so small that there won't be more arrivals in addition to what this says. Okay? So if we use X notation, right, which counts the number of arrivals over any given interval. So the first thing that you are going to write what? Number of arrivals over this interval, which is from 0 to S1, equals 0. Right? Now number of arrivals over this small interval, which is number of arrivals X over small interval, means from S1 to S1 plus delta S1, equals what? 1, exactly 1. And then what do you have? Where should I write? Maybe one after another. Now no arrivals in this place, so that interval starts from S plus delta S1, goes to where? S2. Right? From S1 plus delta S1 to S1 plus S2. That's good. S1 plus S2. Right? There are no arrivals. And then here, in the small interval, there will be exactly one arrival from S1 plus S2 to S1 plus S2 plus delta S2. Am I right? This should be 1. And you can see, you can write one empty, one full, filled, large and small intervals, counts of them, right? Okay. We are running out of time, so I'm not going to write everything in detail, but just give the general idea. Why did I do that? Well, now see, these intervals from 0 to S1, from S1 to S1 plus delta S1, this and that, they're all disjoint. Right? They are all disjoint. Therefore, the number of counts of Poisson events over these disjoint intervals are all independent. Right? Therefore, these events are independent. Therefore, the probability of these joint events, right, probability that all these events jointly happen, equals to the product of probabilities of individual events. Right? And the probability of that there will be no arrivals here. We know the formula for this because this is Poisson distribution. This also has Poisson distribution. I can write down that. We then write this probability as the product of the Poisson probability mass function evaluated at 0, 1, 0, 1. Of course, the rates also depend on the length of the intervals. These are small intervals. These probabilities will actually simplify to like lambda. What was the simplification for the earlier one? It was lambda times the length of the interval. For this one as well. Everything on the second place, you will get a simplification of that kind. And they will survive. You just simplify all these things. There will be lots of cancellations. Okay? And then you will get, at the end, something like this. You will get lambda times e to the minus lambda s1 times lambda times e to the minus lambda s2 lambda times e to the minus lambda s, pardon, this should be lambda delta s1, let me say lambda delta s1, right, because it's the length of the interval. Okay. Oh no, I'm sorry. No, if you just try to jump over it, I have to just guess the density function, of course. It is S1, sorry about that. It is S2, and this is Sn. And then you multiply by the length of the intervals. Actually, there is another term. If you do all these cancellations, let me just write the final results so you can fill in the details, but at least at the end you can check the final result. So you have all these things times e to the minus lambda delta Sn, okay, and then of course this thing as usual. So everything just simplifies to this one. So we want to see this part because that's indeed the density function of n random variables over there. So I haven't divided by the length of the intervals yet, so let me also put them here. Delta Sn, right? This is always there. Plus this negligible terms. Okay, you get something like that. And then what do? You divide the left-hand side by this, so this will cancel if you divide. Of course, you divide the right-hand side as well. So this cancel, and here you get a division by the product of the length of small intervals. Then you let n go to infinite. You let delta S1 times delta Sn, or I guess it is better to say the maximum of all these things, so that all of them go to 0 at the same time. Right? If the maximum goes to 0, of course, all others must also go to 0. You let this thing to go to 0. You take the limit of both sides as this thing goes to 0. This disappears, and these do not depend on delta, any one of delta S's. There is only one this left, but this, if the maximum goes to 0, this must also must go to 0. Therefore, exponential term becomes 1. It just becomes 1. It just disappears. It just, of course, doesn't become 0. It becomes 1. So you get this. And the conclusion then becomes that this joint probability density function, after the simplifications, is lambda times e to the minus lambda S1 times lambda times e to the minus lambda Sn. And what is the conclusion? Then you recognize that each one of them are density functions, and the joint density function, you know, that can be written now as a product of these functions which depend each of these arguments alone, okay, And that's just the indication that actually S1, S2 are, first of all, independent. And then since all of these functions have the same appearance, actually the same appearance as the density function of an exponential random variable or exponential distribution with rate lambda, you conclude that they are also identically distributed. They all have the same density function. And as we just said, since now we recognize the density function, we recognize that it belongs to exponential family, family of exponential distributions, exponential random variables, and for an exponential, to specify an exponential random variable distribution completely, you have to identify its mean, which is 1 over lambda in this case, with mean 1 over lambda. Huh? Something like that. Okay? Try to fill in the details yourselves. We will do another shorter derivation next week. There is another fundamental distribution. Otherwise, the details are also in your textbook. Okay? If you have any questions, you can also find me if you want to go through the details. Any other questions? Okay. Okay, I'll see you next Tuesday. If you want to write your exam one more time, just make sure to do that by Monday and bring your paper to me Monday. All right? I'm going to post the questions on course homepage.